Okay, good evening, everyone. Now we will continue our previous book reading session of Quantum Optics by Mark Fox. And today we're gonna discuss about section 2.2, the diffraction and interference effects, and then we will continue by Handoko, who will explain about coherence, right? So before we dig further in these topics, I would like to reviews our previous discussion about the timeline of the quantum optics. Yeah. Well, it may well known before the quantum optics, the era of photon was defined. We see the lights as the electromagnetic waves. It is due to the demonstration of the wave nature of lights by Young interference experiments in 1801 and the Fresnel diffraction in 1815. And it is further strengthened by Maxwell using the theoretical foundation, his derivation on the electromagnetic waves, which describe more perfectly the wave nature of light itself. So up to this point, the corpuscular theory, which were proposed by Newton, was abandoned at the time. So people see the lights as a waves rather than some kind of particles. Right? Now, and in our previous discussion, we also talked about the solution of the Maxwell equation itself. And then in the previous discussion, we have the harmonic wave ansatz such that we can describe the electric and magnetic field oscillation as the harmonic function, sine or cosine function with respect to position and time. So it oscillates in space and time according to the first two equations. But in our discussion today, and maybe in our next discussion later, I would like to use another definition of the wave function, which is the complex function, so that instead of describing them as the sinusoidal waves or sine function, I use a complex function, which is the exponential complex function. And this equation, the third, what's the pointer? The third and the fourth equation describe the oscillation of the monochromatic plane wave. Why this called the monochromatic plane wave is because we have a single value omega here. The omega or the frequency of the wave itself is single value and it's a constant value. It doesn't change when the light propagates. And we described it as a plane wave such that we have the wavefront of the wave itself. They kind of form some kind of planar plane, a linear plane like this, so that this line, the black and white line, is the wavefront of each of these wave when they propagates. And here the variables k is the wave vector, which determine the normal direction of the wavefront itself. So when we have this wavefront, the direction of the wave vector is perpendicular to this wavefront, such as these red arrows. Here is the wave vector of this plane wave. On the other hand, if we have spherical waves like this, the wavefront is shaped circularly like this one, or spherical in general. The wave vector itself points at the radial direction like this, because the radial direction itself is, perpendicular to the circumference of the circle, right? And the magnitude, the total magnitude of the wave vector itself, as defined in the previous discussion, is basically equals to the wave numbers 2 pi divided by lambda 0. But here in the equation 5, I use much more general definition. I add the variable n here, which describes the refractive index, so that this wave vector is the wave vector in some kind of media other than vacuum or air. Okay, up to this point, is there any question or comments from you guys? Oh yeah, maybe some of you might ask the question, why I have to describe the complex function for the monochromatic waves? Why not just use the sinusoidal function, right? Basically, it is due to the fact that it is much more easier to manipulate the complex function. It is, my motivation is purely based on the mathematical point of view. Down the line, when we talk about the diffraction or interference, we will do a lot of calculation and doing calculation in complex function, especially the exponential complex function, is much more easier. But we have to take a note here. We have to be careful because electric field and the magnetic field itself is a physical quantities which have a real value function. So after we did some nasty calculation down the line, and then we get the final form of the complex function, which is the end of our calculation, we only take the real part of this function. And that is the real value of the electric and the magnetic field itself. And what about the imaginary part? Well, up to this point, I think we don't have to deal with the imaginary part very deep. But later on, when we talk about the lossy media, the medium where the electromagnetic field itself will experience some kind of energy loss, dissipation, the imaginary part will describe that kind of loss. Okay, that's why I use this complex value function. Okay, is it so good? All clear?
So far, so good.
What about Handoko? Handoko, you good? Before I continue.
I think he's having some connection problems.
Ah, I see. So yeah, well, maybe I will just continue. Okay. Now we talk about the interference. In the books, the Markov books, before they talk about the interference, they talk about the diffraction first. But I kind of changed the sequence because it is much more easier to see the diffraction as some kind of interference phenomenon. Personally, I deal with interference first when I study the elementary physics. So yeah, I will explain it much better if I use this sequence. So the interference is basically when we have one or two likes, one or two or three or so on and so forth, waves with phase difference, and they merge with each other. They will create some kind of new waves, which can be much more stronger than in the initial waves, or maybe they will vanish, right? And that depends on the phase difference between each of these waves. There are many kind of interference experiments, and the most famous one is the Young double slit experiment. But here in the Markfords, they use the Michelson interferometer setup. And this is the simple Michelson interferometer setup, which use the 50-50 beam splitter here. Yeah, so when we have some kind of source of light, yeah, the source of light, the beam from the source will go incident into the beam splitter, and this beam splitter will split the light into two beams. The first one will go up into the mirror M1, and the second one will go to the right to the mirror M2. And each of these beams has the same energy, hence they have the same amplitude with each other. That's why it's called the 50-50 beam splitter. And then we can express each of these electric field amplitude of each beams with these three equations. E in is the initial lights from the source. E1 is the first light that go into the mirror one. It has the half of the amplitude of the initial source, and then it has a phase shifting here. And the phase shifting itself is equal as much as twice as the path length that the first light experience here. Why it is equal to 2? It is because the beam, the first beam here, not only go up to the mirror, but also after it go up to the mirror, it will be reflected back to the beam splitter before it being combined again with the second beam. That's why it experiences the path length as much as twice as the distance between the beam splitter and the mirror. And the same thing goes also applies to the secondary beams here. With the length or the distance between the beam splitter and to the mirror is equal to L2 here. But also, one interesting thing about this book is that it adds this phase shift, which is equal to the delta of phi. Delta of phi is the phase shift between each of the beams which happens not only because the path length difference, but because of another factor. And one of the factor that may put into example into this is the phase shifting due to the reflection of some media. Well, I have an animation to describe this phenomenon here. Here I have the lights which travel to the right. The left line is the thinner medium with smaller refractive index, and the median on the right has the thicker medium and the larger refractive index. When the lights from the left go exactly meet at the interference of the interface of this media, it will experience a phase shift. As you can see here, the amplitude is initially facing up, but after it being reflected, the amplitude is being shifted into what we call facing down. Like, this is one of the example of the phase shift due to some phenomena such as reflection. That kind of there are of course any other kind of phase shifting which maybe happen in this setup, and this term delta phi is used to accommodate that term. Like, okay, is it so clear so far?
What is the typical phase shift from reflection? I think it was around pi/2, right?
Either pi or 2 pi. Yeah.
Okay.
Usually when you have the case where when the incident light coming from the thinner media to the thicker media, the phase shift will be pi, because just like the animation I showed before, initially we have the amplitude goes facing up, and then it will be shifted back facing down after the reflection. It means that it experienced the phase shift equal to pi. If we use the sinusoidal function here, if we use the, let's say, the cos pi is equal to 180 degrees, right? The cosine here will be -1, and then multiplied by the amplitude. The amplitude become negative. That's why the amplitude become face down after the reflection. But if the incident media, the initial media, has a thicker characteristic and larger reflective index, when it being reflected in the interface, it doesn't experience the phase shifting. So the phase shifting will be equal to 0 if the light is coming from the thicker media, like that. Okay. Any other question or comments?
I don't know, but as far as I can remember, it was for beam splitter in particular, it experienced around pi/2 phase shift.
Well,
and perhaps I can share some link from Stack Exchange for further discussions.
Yeah, you said that, because what I just explained is just some basic interference,
because I think the one that the example that it shows is that you just showed is the one that the wave is reflected to the direction of the source.
Yeah, right.
For this one, it is reflected like 90 degrees. So I think the phase difference is not pi or 2 pi. It's, let's say, it's pi/2.
Yeah, and one more thing that I might add, that it may experience the phase shift when the lights come into the beam splitter, because the beam splitter consists of 2 interfaces, right? That's the thing that I did not consider in my previous explanation. So, so please send the link so that I can learn much more deeper about the phase shift in this kind of beam splitter setup. Okay, any other comments or question? No? Handoko?
Sorry, one question actually.
Okay.
So here, the equations you used for both E1 and E2 are pretty much based on the previous equations you mentioned, right? The previous slides. It is just that it is in the form of, since you differentiate between the L1 or the position parameter here and the other phase parameter in the delta phi factor.
What? I can hear you.
Sorry. So here you use the pretty much the same form, right, as the previous equation you mentioned in the previous slide.
Oh, this one. Okay.
Yeah. It is just that here you strictly differentiate between the position factor and the other phase parameter that you mentioned.
Yeah. Well, actually, the term of this phase shift, we may include it here, just like this one. In this one, we not only include the position factor here and the time dependence of this function, but also some kind of phase constant. So we may also add the phase constant here to make the equation more general. Okay. But as you can clearly see here that why there is a term of 2 multiplied by L1 here. It is due to the fact that there is a contribution of the propagation direction by the position factor L. So we just plug it in this equation. R position factor R can be we can set that the position factor R with the origin of 0 here, like this is the point where you have x equal to 0, y equal to 0, and z equal to 0, and then the first mirror have the position factor of y equal to 1 and L1 I mean. So that's why we use this kind of phase shift. So it's basically just the function of position.
So can I say that in the issue here, you kind of redeem the omega t and this other psi factor there into this delta phi then?
No. The omega, I remove the time dependence of this function because we only determine the amplitudes of this phenomenon.
Right.
And why is that possible? Because I use the assumption that when the beam are being split into two, it doesn't experience some kind of wavelength shifting. If it does experience wavelength shifting, then the frequency will also change. That's why the omega will also play into roles here. But since the omega is just the same between the first beam and the second beam and the initial beam, yeah, I just cancel that out. Okay? I did not use that.
Yeah, sorry, I missed that. Okay, thank you.
Okay. Any other comments or question?
So far, so good.
Okay, thank you. Okay, let's then we proceed into much more mathematical description of it. So, yeah, previously I mentioned that here the equation 6 to 8 is the amplitude of each of these beams, the initial beams, the first beam, and the second beams. And the interference will only create the beams, the output beams here. It's basically just the recombination of first beam and the second beams. So we can just do a summation of their wave functions, and this is the summation detail of their wave function here. And the resulting equation is the equation 9. As we can see here in the equation 9, we can see the term, although initially they coming from the same beams, right? Coming from the same source, the resulting recombination of each of them doesn't exactly back into E0, right? The initial beam is have the amplitude of E0, but the output beams, which is basically the combination of beam 1 and beam 2, not only equal to E0, but we have some nasty term in within them, right? It is because although they coming from the initially the same beams, they experience the phase shifting due to the fact that they travel a different way, like that. So here we can see from equation 9, we have delta L here. The delta L here is the difference between the first beam and the second beam path length. And here K is the wave vector or wave number, the magnitude of the wave vector in the vacuum. And we can determine the maximum interference and the minimum interference from this term alone, this phase term. The maximum interference means that the beam will construct with each other so that they create a stronger beam, and the destructive or minima happens when they destroy each other and there are no other lights, so that we see the dark pattern in the screen. We can use the Euler formula here in the equation, right? So that we can change this term into the cosine and sine function. We can put them into the real valued function here, the cosine terms, and the imaginary part, the sine function. And as I mentioned before, since the electric field itself, the physical quantity which has the real value, so we can determine the maxima and minima by the cosine value alone. The maximum of cosine happens when the cosine is equal to 1, right? So it's so that's mean the angle of the cosine itself here, the term here, must be equal to the multiple integer of 2 pi, which resulting in the equation 11. And the minima happens when this equation, the amplitude of the output field equal to 0. And that may happen if the cosine function is equal to -1, because -1 plus 1, yeah, it add up to 0, right? And when the cosine is equal to -1, the angle of the cosine itself must be equal to the multiple integers of pi. That's why we get the condition of the equation 12 here. So the equation 11 describe the maxima interference, and the equation 12 here describe the minima interference. And m is an integer starting from 0. Okay. Is there any questions over? It's just the mathematically description. That's why I like the complex value function. We can use this Euler formula to extract some useful numbers.
Yeah, perhaps can you go back to the previous slide?
This one?
Yeah, so what is E naught then?
EO is the initial field amplitude.
Okay.
Okay. The first beam has the half of the initial field amplitude, and the second beam has the other half, because this is 50-50 beam splitter. Okay.
Okay.
Any other question? No. Handoko, maybe? Yeah. Okay. Good. Then we will move again into the typical application of the Michelson interferometer. Yeah, from this equation, we can clearly see that this equation, either the condition of maxima or condition or minima, they highly depends on delta L, right? The path difference between each of the interferometer paths. So we can do an experiment by changing one of the hand only. Like we change the value of L2, and when we change the value of L2, like put the mirror further or closer to the beam splitter, the pattern of the interference itself will change over time. The position of the dark and bright fringes will move, and from the movement of their position of bright and dark fringes, we can calculate some kind of parameter like dilute gas refractive index, where we can get the dilute gas refractive index from this equation. I recall this equation 5. Yeah, the wave vector is not only depend on the 2 pi per lambda, but also it multiplied again by the refractive index. So if we want to measure the refractive index of some material, we just can multiply the first term by m, which is just the refractive index. And then we will get some kind of linear equation. Right? This is a linear equation. We vary the L, and then we can do a linear regression based on the data to calculate the exact value of the refractive index based on this experiment. It is a very useful experiment, in my opinion, because yeah, the data itself is linear, so that we can do the linear regression. Very easy to analyze the data. Okay. Any question or comments? No? Okay. If no question, I will continue to the diffraction part. Well, about the diffraction part, the simple setup about the diffraction is the single slit diffraction, so that we have this kind of slits with the width of the slits is d here, and then we have a screen, and then the slit and the screen are spaced with length L here. L is the spacing distance between the slits and the screen. The diffraction happens when we have the incident light coming into these slits, and then it will experience some kind of wavefront changing like this, based on the Huygens principles. So that when we have initially the plane wave, when it moves past through the slits acts like a new source for the waves, and then the new waves will be generated as the spherical waves. And each of the spherical wavefront will then recombine again at the screen. That's why it will, and remember, previously we talked about the interference when we have more than a wavefront combined to each other, they will create an interference. That's what we call the diffraction. So basically the diffraction is the interference of light with the light itself, due to the fact that when it moves through the object or a slit, it will change its wavefront, such that each of these wavefront may merge with each other. Okay. Yeah, you may see the animation here, the changing of the wavefront from the plane wave into the spherical wave in this website. It's very useful website. Now, we can define the diffraction, distinguish the diffraction into two kind of diffraction. The first one is the Fresnel diffraction, and the second one is the Fraunhofer diffraction. We may recognize the Fresnel diffraction as the near field diffraction, while the Fraunhofer diffraction is the far field diffraction, which is basically usually included in the fundamental physics textbooks. We can define the Rayleigh distance as the square of d divided by lambda. Yeah. And then we can see which of this which kind of, or what kind of the diffraction may occur based on the length or the distance between the slit and the screen. If the distance is larger than the Rayleigh distance, yeah, then we call it the Fraunhofer limits. The diffraction may occur in the far field region. But if the distance between the slit and the screen is much more not much more, is lower or equal to the approximately equal to the Rayleigh distance, the diffraction itself became the near field diffraction, or it will go into the Fresnel region like that. So it's just basically on the length of the slit and the screen distance. But there is another things in the Fraunhofer limits that we may exploit. Basically, as I mentioned before, the diffraction itself is just an interference of this wavefront in the screen, right? So that we can calculate we can determine the maxima and minima pattern, the bright and dark pattern, using a summation of each of these waves. But the difference between the previous interference phenomena, which I explained using the 50-50 beam splitter, and the interference which happened because of the slits, is that the slits acts like a infinite point slits, so that it acts like an infinite number of source of light. That's why when we do the summation of each of these fields, we don't do the literally summation as previously, but instead we did an integral here. Okay, because there are infinite numbers of wavefronts which are coming into the screen, like, and yeah, actually the derivation of this until we can get the intensity pattern on the screen, maybe well explained in the another textbooks of optics or fundamental physics textbooks. But here I only take the final result of the equation. The equation 14 here describes the intensity of the diffracted light on the screen. Yeah, as we can clearly see here, it depends highly on the beta, and beta is depend highly on the slit dimension d here, and the theta. Theta is the angle of deflection of the beams from this slit here. Okay, So based on this equation, we can determine which point on the screen which will produce what we call the bright pattern or a dark pattern. The point of the theta equal to 0, which is basically the center of the screen, will always have a bright pattern of this diffraction phenomenon. We call this point maximum principal maximum. Okay, and then the minima may occur when the beta is equal to m multiplied by pi. Why? Because if m is multiplied by pi here, the sine function here will be equal to 0, right? And if the sine function is equal to 0, the intensity is equal to 0. We intensity equal to 0, which means that we don't have any lights. It's dark. That's what we call the minima. And there are another maxima, the subsidiary maxima, which occur when beta is equal to this equation. And the beta is, of course, an integer, right? The subsidiary maxima will have some kind of decreasing amplitude compared to the principal maxima here. So that the further it is from the center of the screen, it will be much more darker. This is the example when we use the circular slit, like circular aperture of diffraction. You can see that the center of the screen here has the brightest spot. This is the principal maximum. But as we go further in the radial direction from this center of the slits, center of the screen, the maxima itself become much more darker and darker and darker. That's why, because from this equation, sine beta divided by beta is just the sine c function. The sine c function has the graph of something like this, some kind of decreasing amplitude. Okay, up to this point, this is my final part of talk. Is there any questions about this diffraction?
Sorry, just one trivial question.
What is?
Can you go to the previous slide? Yeah, here it is mentioned that the principal maximum occurs at theta equals 0, right?
Right.
But I get that from the mathematical analysis that, yeah, it is producing the principal maximum when you take the limit as the theta goes to 0, and then, yeah, you create the principal maximum there. But at precisely theta equals 0, we see that, yeah, it will be indefinite, right? As beta will be equal to 0, and then the I will be indefinite. So is there perhaps some kind of explanation maybe why theta equals 0 here is supposedly indefinite, but yeah, here you take the limit and then, yeah, it creates the principal maximum.
Yeah, well, basically I don't really know the details about the sin c function, sine c function. Well, sine c function is kind of approximate function, and it is very mathematical aspect why that function is defined in such a way that when the angle of the sine itself is equal to 0, it will create that this value of the sine is equal to the maxima is equal to 1 usually. So in that kind of sense, I cannot give a much more better answer than yeah, that's just the properties of the science. But in the physical sense, yeah, when the theta is equal to 0, it is located at the center of the screen, right? And basically, the center of the screen is have the same location as the whole of the slits. So we can clearly see that each of these light that enter the slit will just pass through this hole, and then it will, yeah, being accumulated here. That's why this is the brightest spot, but what we call the principal maximum. That's from the physical point of view.
Okay.
Can I add something to your explanation?
Yeah, please.
Yeah, as you can see from equation 2.2.14, I theta is proportional to sine beta over beta squared. if you remember in calculus classes, the limit as beta goes to 0 of sine beta over beta is equal to 1.
Yeah.
Yeah, so it is essentially what is happening on the screen. So we don't exactly know what happens when theta is exactly equal to 0, but so far, as far as we are concerned, it is good to say that the intensity is maximum at theta equals 0.
I see. Yeah, it's a very it's just basically just approximation function, right? But yeah, in another sense, I have another explanation regarding this. When let's say that beta is literally equal to 0, right? This let's say this term will explode into a very high value, and then it will create a very high intensity, right? So it will create a very bright spot. But no, yeah, that's just yeah, we cannot use that description. But as Farhan mentioned, it is a limiting function, and then we cannot know for sure exactly what happens at beta equal to 0. But as it approaches 0, we can clearly see that, and from combined with the physical point of view, that we can clearly see that this location in the screen has the brightest spot. Okay, that's just yeah what I can give, what the best thing that I can give you right now. Okay, any other comments or question maybe? No? So good? Okay, if you are good, then let's proceed to the next section, which will be presented by Handoko. He will talk about the coherence properties and the coherence of light. So Handoko, please. The time is yours. Hey, you are still muted.
Oh, sorry. Can you see my screen now?
Yeah.
Okay. So continuing Dharma's lecture on this subject, I'll talk about what is called coherence, which is perhaps new for some of you, but yeah, this is pretty much one of the most important concept in quantum physics or quantum optics itself. So here, Dharma previously talked about this Michelson interferometer, right? But on the previous discussion, Dharma assumed that during the interferometer process, the phase difference between the E1 and E2 here, which I referred to the E1 refers to the light going through and back to the BS from the L1 route, and E2, which goes through the L2 route here, is only due to their path, optical path difference, right, which is equal to 2 delta L. Here, coherence basically helps to describe the effect of the other factor that Dharma previously mentioned. It is the delta phi factor there, one of which is the frequency range delta omega here, which is possibly washing out the interference pattern there, because yeah, as you can see from the previous equation, the interference itself heavily depends on the phase difference, right, between the two of the electrical field here. Okay, so the formal definition of the coherence itself is basically the property that describes the stability of light, or others can also say that it is the ability of light to produce the interference pattern here. So we can say that two light are coherent when they can produce a good interference pattern. Yeah. And we see that coherence itself is classified into two kinds or two types. Here it is the temporal coherence and spatial coherence, but in this book, for now, we will only discuss about the temporal coherence. So there's a important quantity in when we discuss about temporal coherence, it is the coherence time, which I use the notation tau c here. The definition of this tau c is the duration over which the phase of the wave train remains stable and is related to its analogous quantity, which is called coherence light. Well, it is pretty much the standard wave, the standard speed and distance relation here, where we can see that LC equals to C times tau C, where C is the speed of light. And yeah, we can also see that coherence time is determined by the spectral width of the light, which means that yeah, tau C is inversely proportional to the delta omega, which is the spectral width. Well, this pressure broadening thing I input here on the right side of the slide will be discussed further in the next subject about the radiative transition. But basically, we know that during the emission and absorption process of the light, atoms collide each other, and this makes the lifetime of the emission and absorption itself become shorter, which in consequence it makes the spectrum becomes wider, like can be seen in this picture. So as the pressure goes higher, the spectral broadening here will become bigger as well. So yeah, and for monochromatic source, a light which is kind of idealized, the delta omega will be equal to 0, which means that yeah, it will create an infinite coherence time here. So is there any questions so far?
Yeah.
Farhan first. Farhan.
Okay. So the equation LC equals C times tau C. Does the equation only work for cases when light travels through, let's say, a vacuum, or is it also applicable for light in a particular medium?
Well, I never thought of that, but I think it is supposedly up. Well, I think we are only talking about the light traveling through the vacuum here, but as for the case when the light travels on a certain medium, I think it should be, wait. Well, I don't know the definite answer for now, but yeah, I'll search for it later because yeah. But it is supposedly different, right? Because it is no longer C there. As the speed of light travels through a medium, it will be affected by the refractive index of the medium, right? So yeah, it is supposedly different as far as I can guess, but I'll search for it later. Thank you.
Yeah, maybe just adding your answer. Yeah, maybe the equation will hold the same because it depends on the delta omega. And when the light travels into some kind of media, it will experience the spectral broadening, which means that the frequencies of the light will not stay the same, but will shift, and it will experience shifting in both ways to the higher frequency or the lower frequency, depending on the dispersive properties of the media itself. So yeah, I think it will also affects the coherence time when light travels in the vacuum and in the medium due to the fact that there are spectral broadenings from the dispersion. Yeah, that's my addition.
Okay. Is there any other question maybe?
Can I ask? May I? And I think I have thought about your previous discussion. As Dharma say that the condition of the material that the light pass through, like the material itself, will affect the frequency, right? As it affects the frequency, the spectral width, which is the delta omega. And I think if it is affect the time, the coherence time, then as the speed of light is also affected. So it will be like canceling each other, and then we'll get the coherence length by the same. I don't know. I've no idea. Just not trying to like ngerjain ini beneran, cuman in my mind, like if it affects the frequency, and we know that frequency is berbanding terbalik with the speed of light. So yeah, do you get what my point is or no?
Yeah. So you basically say that since light travels through a medium, like Dharma said, it will affect the frequency, right? And frequency itself is pretty much related to the speed of light, which you said before. It is proportionally berbanding terbalik, right?
Yes,
So
and sorry, and yeah, so by the equation LC equals to C dot times tau C. So if tau C changes, also the C is changed. Yeah, maybe the is the coherence length will stay the same.
Well,
Well,
Dharma first.
Okay.
yeah, maybe my main question is in the media, not vacuum, right? Does the equation LC is equal to C multiplied by tau C? We still use C, or we change the equation into speed of light in the media V. I mean, if we still use C, then when the coherence time changes due to the spectral broadening effects in the dispersive media, then of course the length of coherence itself will also changes. But if we use if we change the C into the speed of light in the media, when the spectral broadening happens and the coherence time changes, it may cancel out. So I don't know which one the definition that we use in the media. So do we still use this equation, or we change the C into V?
I have another opinion. I think LC is equal to C times tau C is a definition. It's a definition that is universal. That is to say that it applies to both vacuum and media, a certain media. But the effects of media of media is only taken into account by tau C. So the equation LC is equal to C times tau C still holds, I think.
Oh, I see. So you mean that although we use other media other than vacuum, we still use this equation and only put into the effect of the media to the tau C.
Yeah.
I see.
Yeah, I think also kayaknya, soalnya this is just a definition, right?
Right. Well, adding to the Farhan's point, I actually agree to what Farhan said. Well, this equation holds for even if the light travels through a medium, but it basically only affects the tau C. Well, perhaps I need to add something in more detail here on why is actually this coherence time affected a lot by this pressure broadening. Well, as we can see, as the light goes into what is called the idealized state of the delta omega equals 0, the broadening itself will get shrink, right? It will become smaller, the width, since it is inversely proportional to the delta omega, right, the tau C. So we can see that as the pressure broadening becomes smaller here, and the tau C will get bigger, and as it goes into 0, the delta omega, the tau C will goes to infinite, which means that it is the idealized condition of light is infinitely coherent or has infinite coherence time. So it regarding the medium itself, it should only affect the perhaps microscopic aspect, which we'll need further studies to learn on, and it basically only affects the tau C here. That's for the definition. And inversely, kebalikannya, kalau misalnya we talk about so many collisions happening inside, or meaning we do the measurements on the high pressure condition, it will make the spectral broadening higher, and resulting in very short coherence time. Okay, so I guess no more question on this part.
Yeah, I'm good.
Yeah. Okay. Oh yeah, here's pretty much an animation showing that the incoherent and coherent light here. As we can see, as the time goes by, as the tau c here is passed, the light will get out of phase, and it will become more out of phase as the time difference increases here. It is pretty much just the animation to describe that phenomenon. Okay. So here we have a quantity, or some kind of quantity that can help us describe the coherence of a light, which is called the correlation function, or we can say that this is also the degree of coherence described or notated by G1 tau here. Here G is defined by the equation shown here. Well, the kurung siku here pretty much means that we take the time average of all the modulus of the electrical field here, summed over a certain period time t here. All right. So we assume that the electric field input here is a quasi-monochromatic with a center of frequency of omega 0, omega naught here. So we see that it has the form of E0 time. E0 like this. It is very much similar to what Dharma previously showed here. And substituting the expression above into the G function there, we get that the correlation functions, which depends on the time delay tau here, will be equal to this. And indicating that the real part of G itself is an oscillatory function, as we can see from the first part of the equation of G here. We can see that the real part is just the oscillatory function of tau with a period of 2 pi over omega naught. Well, if we want to derive it, we can use the Euler formula there, and we took the cosine part of the real part here. And we can see that from the equation G here, when tau is precisely equals to 0, well, of course, the G itself will be equals to 1, right, for all cases, because it pretty much means that there is no time delay at all, and the light would be perfectly coherent one to another. And when the tau, or the time difference, is between 0 and tau c, we can see that the phase t plus tau here will be approximately equals to the phi t itself, as the definition of the coherence set itself, or the coherence time. It is a property that describes as long as the light is still on the coherence time duration, the light will still stay in phase, basically. It will preserve the constant phase. And of course, as the tau increase, as the time delay goes even higher, the G will eventually decreases a lot as well, which will eventually leads to this phi t plus tau will be completely unrelated to the phi t itself. Okay, perhaps is there any question up to this point?
Well, I'm just curious about this first order correlated function, correlation function. Do you derive this equation from the perturbative point of view? Because it is very similar to the first order perturbation correction in the quantum mechanics. I mean, just the equation just looks similar.
Well, I actually tried to look for the origin of this. You mean the equation in the first line, right? The G1 tau equals to the sum average of the modulus and divided by the modulus squared. That one.
Yeah, that one.
Yeah. Actually, when I tried to look everywhere, it just started with this definition. So I didn't really. Well, I get your point where this equation is really similar to the perturbation. effect. But yeah, I need further look on this for the origin. But for now, the definition of the coherence function itself is defined by this equation. So yeah, sorry, I still cannot answer that question.
Yeah, let me add something.
Hmm.
I think as how it is called as first order correlation function, I think it is essentially a perturbation theory. Perturbation theory in general is a series expansion of something, some quantity, let's say. So the first term, which is the first order correlation function, is the most dominant term, and then the second order is less dominant and can be neglected in many cases, and the third order is even smaller, and so on and so forth. So I think, yeah, I read a paper that says something like second order correlation function in the past, but I don't seem to really remember it. But I think, yeah, I'm very convinced that this is essentially perturbation theory. Perturbation theory is essentially series expansion, like expansion by using Taylor series.
Right. But actually, as I made this PowerPoint, I saw in the book that the second order approximation will eventually be discussed as well in the future of the book. But yes, as for now, the introduction to the coherence itself will only discuss the first order correlation function only. But we will eventually get into the second order and perhaps the further approximation as well.
Yeah, well, and what may be interesting is that in the case of the quantum mechanics perturbation theory, we have what we call the degenerate case, the degenerate case. And yes, the second order may be very small, but if the first order have some kind of degeneration, we may use the second order collection.
Yeah.
And yeah, maybe I don't know. Is there any kind of some kind of degeneration in this correlation function of the coherence of light? That would be a very interesting topic to discuss later. Yeah, that's just some comments. Okay. Yeah, please continue.
Yeah, right. So is it okay for this slides from Difa maybe?
No,
Okay.
good. Thank you.
Okay, continuing this. Yeah, we still talk about the first order correlation function here. So as we can see, as we will about to see, the correlation function here for partially coherent light in particular depends on the type of the spectral broadening that applies. So here's another spoiler for the next subject to come in the future. Spectral broadening is not only caused by the pressure broadening, like I mentioned. There are, pretty much as far as I know from the atomic physics, there are three types of the spectral broadening. One of which is the natural broadening, spectral broadening, and the last one being the what is called the Doppler broadening. But yeah, for now we won't talk about that as it will be discussed in a lot more in the future. So yeah, here's just some example for the case. Let's say we have the Lorentzian line shape of the spectral width here. For the light with the Lorentzian line shape of the half width delta omega here in the frequency angular unit, the correlation function takes the form of equation you can see here in the slide, where the tau c here, as you can see, is always approximately or always inversely proportional to the delta omega. And the equivalent form in the Gaussian line shape formula would be, what is shown in the slide there as well. And especially for the Gaussian line shape formula, the tau c will be described by this equation. As for why it is like that, I think it will also be discussed in the broadening lecture as well in the future. And so we will also be introduced to a certain property called the visibility of the visibility here. So visibility for now is described as the ratio between the difference between the I max subtracted by I mind here, Imax being the maximum intensity and Imin being the minimum intensity recorded in the spectrum, divided by the summation of both Imax and Imin here. So yeah, for now, we will see that the visibility property here, as previously mentioned, will be pretty much correlated to the correlation function itself. So yeah, we can see that for a light with average constant intensity, the fringe pattern will only depend on the time difference tau between fields, and the output field itself can be written as 1 over square root of 2 times the difference in electric field output here. Well, this 1 over square root of 2 term comes from the previous discussion as well, where we assume that the beam splitter splits equivalently 50-50 ratio of the light splitting through the beam splitter previously mentioned. So if we take the time average, we can see that from the previous discussion as well, where I is proportional to the modulus squared of the electrical field. And yeah, through the mathematical derivation, we can see that this I takes the form of equation shown here. And yeah, as you can see, the third and the fourth term here is pretty much just a complex conjugate to each other, right? So if we sum both of them, we can see that from the complex number identity that a certain complex number z plus the z star, which refers to the complex conjugate, will be equal to 2 times the real part of the complex number itself. And yeah, we finally get the form that I will be proportional to this, related to this equation here. And so substituting this G1 term into the expression above will result in the relation shown here. It is the I as a function of tau will be equal to I naught, in which I naught here refers to the initial input of the light before it comes into the beam splitter, times the 1 minus the real part of Z1t here of the correlation function, where we also substitute the I max and I minus into the visibility function previously mentioned, where we substitute that the I max will use the plus and the minimum will use the minus. This can be described by the fact that the cosine function takes the value between the -1 and 1, right? And it is at maximum when it is equals to 1, and reverse it will be minimum when it is equal to -1. So if we substitute this into the previous visibility formula through the mathematical derivation, we can see that the visibility itself is pretty much equals to the correlation function itself. Hence, the visibility itself will also be a description of how coherent the light is. And I guess that's all from me, I guess. Oh, sorry, is there any question?
I'm still don't have any question yet. Maybe Farhan or Difa have question.
No, I don't have any questions.
And
I just curious which what thing that can be measured in here, like is it the time of the tau or the burning spectra, the delta omega?
Sorry, I didn't really get your question.
Like what can we what can we measure first to know this such a thing, even the tau first or the delta omega first?
Well, I think Farhan is much more experienced in that.
Yeah. I never really do any experiment on the visibility
Well,
part here. So yeah, Farhan may have
This is
further.
what
I think
to be measured.
the one that we measure in experiments is actually the intensity.
Yeah.
So the equation from the previous slide, the visibility goes to I max minus I min divided by I max plus I min. This is the one that we use. We typically use in experiment. This is the one that I used personally in my previous experience. And perhaps by using this equation, we can acquire the G1 tau. Because, yeah, it is very straightforward in experiment, right? Also, another interesting thing from your previous explanation is the spectral broadening from Doppler shift, like Doppler effect. So I think that's essentially redshift, right? if you know anything about astronomy, like light
that's
from
what we learned.
yeah, light
Handoko.
from moving objects can experience redshift from blue shift. Redshift is essentially the light will be shifted to lower frequency, if the object is moving away from the observer. The opposite occurs, and the process is called blue shift.
Yeah, that's true. Will we have a discussion on that, Handoko?
Yeah, we eventually will. It will be discussed quite a lot in the next chapter, which is chapter 3 about radiative transition, because we will talk a lot about how the transition actually occurs between the electronic state of the energy level, and we will eventually come into the spectral broadening, which, if I recall correctly, it will be 3 of them: the natural, pressure, and the Doppler broadening. Right.
Okay, thank you so much.
Maybe adding up some kind of broadening spectral broadenings. We may as well discuss later about the spectral broadenings, which happens due to the nonlinear effects, which is my field.
Nice.
There are so many useful applications in spectral broadening from the nonlinear point of views. And one of the most interesting things that I still study right now is the stimulated Brewang scattering, which can induce shifting to the frequencies to the higher or lowers due to the coupling between photons or light waves to the sound waves, the phonons in the materials. So there are many kind of nonlinear process which can induce the spectral broadenings, and stimulated Brewang scattering is just one of them. But well, we will discuss about this when we reach the part of the nonlinear optics. Okay.
Actually, I have one question myself. So Farhan, perhaps especially. Yeah, we see that. Well, I did read about the definition of the visibility itself, right? So it is pretty much the IMX minus IMIN divided by the IMX plus IMIN, right? It is the formal definition, but is there perhaps any other physical interpretation on this visibility, like besides it only, so if the visibility is high, it means that the coherence will be also high as well, as we can see from the relation that the book has derived. The visibility is pretty much equal to this coherence correlation function, right? Or is there another thing that you can add here, maybe?
I don't think there is anything to that.
Okay.
Because visibility is a quantity that measures how let's say we want to acquire a maximum interference pattern, and visibility is a quantity that measures how well our interference pattern is, like how if it's 100%, that means that the interference is 100% constructive. We get a maximum interference, and usually, like experiments particularly in quantum information, we usually require the visibility of at least 99%, and it's very hard to get. So we want in our experiment in quantum optics to be as ideal as possible. So that's why a minimum feasibility of 99% is required. But I don't really know about other fields of quantum optics. But for quantum information, I think that is the typical feasibility that we want. Because to do quantum information, let's say by using entangled photon pairs, the number of photon pairs that is produced by some process, let's say from spontaneous parametric down conversion, the number of photons that are entangled are much smaller than the photons from the source, from the laser. So we wanted to have the visibility to be 99% at least.
Interesting.
And it's very hard to get the visibility of 99% in experiment. It takes very long time to move from 98% to 99%.
Wow.
Wait. Can the feasibility up to 100%?
I don't think so in experiments. Usually, it depends on how accurate your measuring device is. Yeah.
I mean, and theoretically,
Theoretically, yes, it can be 100%.
Okay.
But in experiment, we always try to make it as much as closer to 100%.
Well, I'm just curious, based on the papers that you may have read, how much is the largest visibility that you have found in some kind of reference?
99 point something.
0.9 or less?
I don't know the details, but at least 99%.
Okay. Because I can imagine some kind of number, but 99.99. Okay.
Okay. So no more question, maybe?
Yeah, I'm good.
So yeah, perhaps to sum up all of this for those of you who are still confused, I will try to describe just a little bit more on the main point about this coherence itself, the basic main concept. So as we can see that the coherence itself is pretty much the property that describes the stability of light. For a single light, it is described by how a light can actually preserve or maintain the phase as the time goes by. And this time on which the light can maintain this stability is called the coherence time, as I previously mentioned. So if we were to visualize it as a certain time passes by from a certain time to time 1 to time 2, as long as this time 1 and time 2 is still less than tau c, it means that the light will be considered to be able to maintain their phase, right? So yeah, the phase will be maintained, but after that tau c, there will be some off phase of the phase of the light itself. And as we can describe, or we can say that two lights are said to be coherent when they can produce a good interference pattern for what certain time tau c there. And it is basically the ability of light to produce the interference pattern, like what Farhan previously said. Okay, I think that's all.
Okay. Thank you, Handoko. So I think that concludes our discussions today about the section 2.2 and 2.3, the diffraction, interference, and the coherence. In the next section, we will talk about the nonlinear optics. I don't know if Difa wants to present. I welcome Difa to do so, but if not, then I will do the presentation about the next section. But if I told you that the third chapter is much more difficult because we now talk about the quantum mechanics in the third chapter. So that's your choice. You choose the third chapter of the last section of this discussion. Anyway, yeah. Well, anyway, let's meet again in the next section and see you guys.
Record, matikan.
Thank you. Okay.